It's all participate to such a nice conference. So the talk of will be on primordial nano black holes. That means that I will concentrate on primordial black holes which are light, and of course we will discuss what that means in the following. So in fact, the idea of the talk is very simple, and it comes from a paper that is published recently in PRL by myself and by my two very good students, Valerio De Luca and Gabriele Franciolini. The idea is to show that if the nanograph 12.5-year signal has to be ascribed to gravitational waves, and there is a big if, of course, then maybe there is a possibility that this stochastic gravitational background comes from primordial black holes in the range of masses where primordial black holes can still be the dark matter, which is quite exciting. Okay, so the motivation of the talk, of course, it's the many merger events that have been seen by the LIGO-Virgo collaboration. There are about 50 events by now in the mass range from a few solar masses or so. So the question is, what is the nature of these black holes that the LIGO and Virgo have seen? So of course there are two options. One is the fact that the black holes are of astrophysical nature. There is a limit, a lower limit on the mass, if that is the case, which is about 1 solar mass. If the black holes are of primordial origin, they are originating during the evolution of the universe, and the basic difference compared to the astrophysical ones is in the mass range. The lower bound is much smaller, about 10 to minus 18 solar masses, where this bound comes from the fact that we want the primordial black holes not to evaporate within the age of our current universe. So there are basically 3 questions which are interesting to ask. First of all is, may the primordial black holes account for the LIGO-Virgo events? Right now, we have done some search recently, and the conclusion is that yes, not all of them, about 20% of them can be still dark matter, especially in the high mass limits where there is the so-called mass gap. The other interesting question is, if both of them exist, how can you distinguish between primordial black holes and astrophysical black holes? This is a question that most probably will be answered by the first generation of gravitational wave detectors, like the Einstein telescope, for instance. And then the other interesting question is, if primordial black holes do exist, can be the dark matter? The answer is yes. If we plot here the mass of the abundance of primordial black holes in units of the total dark matter abundance as a function of the mass of the primordial black holes, there is still a region here that is indicated by green, which goes from 10 to minus 17 up to 10 to minus 12 solar masses, where this ratio can be unity. So that means that in principle, if we concentrate on very tiny, very light primordial black holes, there is a possibility that in fact the primordial black holes, they comprise all the dark matter that exists in the universe, which is quite nice. If you go to higher masses, especially in the LIGO-Virgo range, this is not so. There is a bound on this parameter FEBH, which is about an upper bound, which is about 10 to minus 3 or so. So where are these primordial black holes coming from? So there was a talk yesterday by Sasaki, so I'm not gonna go into very much details. Primordial black holes may form, this is only one option, may form from the collapse of large overdensities in the early universe. If they are larger than a given threshold, then they collapse almost spherically. And the energy density fluctuation is proportional to the Laplacian of what is I call here zeta, which is a curvature perturbation, which may be originating in fact from inflation. So the idea is that the most understudied scenario is the one that I will use in the following, which is the fact that there is a period of inflation where the universe is exponentially expanding. So the scale factor is exponentially growing as a function of time. And then if you have a potential that goes out of the zero roll phase, the usual standard zero roll responsible for the CMB anisotropies, there is a non-attractor phase, which is indicated here in green, where basically the potential is extremely flat, so flat that the the formula for the curvature perturbation, which has a 1 over phi dot denominator, since phi dot basically goes to 0, there is a kind of, the potential is almost irrelevant in the equation of motion. And then the curvature perturbation power spectrum can grow like the number of efforts exponentially. And this power spectrum has a boost basically at very small scale. So that's basically the idea, one of the ideas to produce primordial black holes. Of course, there is some fine tuning because you need to produce the primordial black holes in the right abundance. But this picture shows that we are dealing with scales which are not similar to the CMB or the last scale structure. Those are very large scales. There, the curvature perturbation is of order of 10 to minus 5 or so. We will be dealing with curvature perturbation which are of order unity at very smaller scales. Okay, so that is the idea. Scales which are basically not tested that much by other experiments. So primordial black holes, they give an opportunity to test also those scales. So the idea is that these fluctuations are beyond some thresholds. There's been a lot of work understanding what the threshold means. Basically, people have understood some time ago that this threshold is not a universal number. It depends on the shape of the power spectrum of the curvature perturbation. I don't have time to go into these details. People have already understood that all process is highly non-Gaussian, or in any case, the non-Gaussianity has to be taken into account because you're looking at the tail of distribution of the production of the primordial black hole. So non-Gaussianity is very relevant. But the idea is that you have an overdensity, and then when the universe is expanding, the horizon does the same. At some point, this perturbation or the wavelengths of the perturbation re-enters the horizon. They were outside the Hubble radius because they were produced by inflation. And at some point, if the fluctuation is large enough beyond some threshold, this fluctuation will collapse and will form a primordial black hole. And then you can compute the abundance of this primordial black holes. This beta represents basically the probability that within a given horizon, you form a primordial black hole. We'll be dealing with numbers which are very small, typically 10 to minus 10, 10 to minus 15 or so. But today, what I want to focus on, in fact, is the byproduct of this almost spherical collapse. So as we have seen, the density perturbation is proportional to the Laplacian of curvature perturbation. If you like, this is nothing else than just a generalization of the Poisson equation, even though in a gauge invariant way. And by the same process, what happens is that when this fluctuation re-enters the horizon in order to form the primordial black hole, it's unavoidable that you also generate gravitational waves. And the reason is very simple, because if you look at the equation of motion for the gravitational waves, which is here in this box, on the right-hand side, you have a second order source. Second order means that it's quadratic in the curvature perturbation. And of course, you have to pay gradients for the simple reason that you are dealing with gravity, which is, of course, a derivative theory. So you have to pay the derivatives of the curvature perturbation. So every time you form you do form a primordial black hole, but even if you have a fluctuation that does not end up in a primordial black hole, you have a production of gravitational waves, which are born as non-Gaussian because, of course, the source is second order. And the idea is, now the question is, can we see those gravitational waves, the second order induced gravitational waves by current or future experiments, like LISA or nanograph. So let me just go a little bit more in detail about the properties of these gravitational waves when they are produced. As I said, when the perturbation is still on super Hubble scales, the source of the gravitational waves is basically suppressed by the fact that you pay a gradient. So you pay a k over h, where h is the comoving Hubble radius. So this is much more than unity. And when when the perturbations are, the wavelength is inside the Hubble radius, you pay another price, which is the fact that for instance, if you are during radiation, you pay the transfer function, which also decays like 1 over k squared. So, and this time k over h is much larger than unity. So 1 over k squared is much more than the unit of the Hubble radius or the Hubble rate. And therefore the production of gravitational waves is highly suppressed. So from this simple argument, it tells you that the gravitational waves are produced at the horizon crossing, okay, mainly at the horizon crossing. That means that the frequencies of these tensor modes will be basically set by the horizon when the primordial black holes they are formed, or in any case when the wavelengths of this peak of the curvature perturbation re-enter the horizon. So once you have understood this generic and intuitive things, then you can compute the abundance of the gravitational wave, which is basically nothing else than the second, the 2-point correlator of the first time derivative of the tensor modes in proper units. Now, a simple computation tells you that in fact the spectrum that you expect for these gravitational waves has the following characteristics. It grows like k cube when you look at small k or small frequencies. And then on the right-hand side, if there is a peak, let's say, so here I'm plotting for the curvature perturbation, which is a logarithmic, which is an exponential evolution. It's a log normal, basically, which is peaked around the scale k star. And for k much larger than k star, it's interesting to notice that in fact the 2-point correlator of the tensor modes is proportional to the square of the curvature perturbation, which is nice because of course you inherit here information about the curvature perturbation power spectrum. Okay, here is the formula for the total omega. It's a little bit more complicated. It's a convolution, of course, because you have to integrate over the internal momenta. If you consider the production, you look at from the particle physics point of view, just a loop. But interesting enough, on the right-hand side of the peak, the power spectrum is basically the omega gravitational wave goes like the square of the power spectrum. So this is important to notice for what I will tell you in a minute, okay? All right, so now the interesting connection is the following. Let's go back to the range of primordial black holes masses, where the primordial black hole can still be the dark matter. So this is the green area here, again around 10 to minus 12, 10 to minus 13 solar masses. This band corresponds to, so there is a one-to-one correspondence between the mass of the primordial black hole, which is formed, which is nothing as the mass contained the horizon. The horizon sets basically the frequency of the tensor modes for the reason I explained before. So this maps into the green region here. And here I'm plotting basically the sensitivity curve for the LISA experiment. And there is a very nice coincidence. The fact that if you look at the peak of the LISA experiments, which is about the millihertz, this will set up, there is no way you can change those numbers. This will basically select a 10 to minus 12 solar mass primordial black hole, which is exactly in the region where the primordial black holes can be the dark matter. So there is a nice correspondence between the frequency of the gravitational waves that can be detected by LISA eventually, and the fact that if you say that those gravitational waves, the stochastic background comes from the second order tensor modes, then there is a one-to-one correspondence between this frequency and the mass happens to be exactly in the range where the primordial black holes can be still the dark matter, which I believe is an interesting coincidence. Okay, now let's go back to the title of the talk, which is this Nano graph. So we have basically a bunch of millisecond pulsars. It's about 45 or so. Whose signal that we collect is sensitive to the presence of stochastic gravitational wave backgrounds. Basically, what is measured is the cross correlation of timing residuals, because we are measuring the time shift of the signal emitted by these pulsars when they are collected. And this 2-point correlator is a function of the gravitational wave strength, of course. It goes like the square of it. And then there is this gamma AB, which accounts from the fact that how these pulsars are, these millisecond pulsars are distributed in space. Okay, so the interesting thing is that the nanograph collaboration have recently published the result of what they call the 12.5 year bunch of data. And they basically see, if you plot the residual as a function of the frequency, they see a common pattern in all the 45 millipulsars, which is given in this figure here. So they basically see a signal which might be ascribed to a stochastic gravitational background. In the paper, they are very, very careful. They never say that, that this signal is a stochastic background of gravitational waves. But they say that if you say that there is a kind of power law in this signal, so there is an amplitude a square and a power law, which I guess by historical reason, they parameterize by phi minus gamma, where gamma is a given parameter. Then there is, you can compute what would be the amplitude of this signal, which is this figure here. Now, interesting enough, there is also, you can do a posterior analysis, Bayesian posterior analysis, to ask yourself what is the typical value of gamma. And the gamma equal 5 is still allowed. So that would mean that if that is the case, then the signal, the stochastic background, would be basically flat as a function of frequency. Of course, this is interesting for what I will be saying in a minute, but of course, there are other options. For instance, that this gravitational wave background may come from a more standard astrophysical black holes, massive black holes. But here I would concentrate for the rest of my talk in the possibility that this signal, in fact, comes from the second order gravitational wave that I described before, related to the presence of this asteroid-like masses, primordial black hole. One more information about this nanograph before jumping into the explanation, into the theoretical explanation, is the fact that, of course, here the situation has to be taken with cum grano salis, as people say. So we are in a situation very similar to, for those who are old enough, they remember that when the data from the COBE CMB came out, at that time we look at the monopole of the background radiation, and then we had to wait many years to see the anisotropies of it. Here we are basically in the same kind of situation. We might have seen the monopole of this gravitational wave background signal, but of course, in order to be sure that the signal can be ascribed to gravitational waves, we need to see what is called the Herling-Dohn correlation pattern, which is basically the fact that the signal should be distributed as a function of the angle, which identifies the location of the millipulsars, which has a given, if the signal is stochastic gravitational wave background, has a given prediction. Now the data are a little bit too messy to, of course, to say anything important about this claim. So we have to wait a little bit more, like not that much, 2 or 3 years, in order to eventually see the pattern or not to see it and disprove the fact that this signal is a gravitational wave. Okay, so having said that, so what have we done very quickly? So we said, okay, we have this range of masses where the primordial black holes can be still dark matter. So what we said is the following. We said, if the curvature perturbation is very flat, so here basically we took a step function which gives an amplitude, a constant amplitude for k between k long and k short. So we basically took an almost flat power spectrum for the curvature perturbation. Then we can compute, of course, the abundance of primordial black holes, which are formed mainly at when the shortest scale is entering the horizon. That can be understood very intuitively, because, of course, I remind you that to form a primordial black hole is a very rare event. So you start forming the smallest one, the one that corresponds to the shortest wavelengths, corresponding to k short. And then in order to form another black hole when the other modes enter the horizon, since the probability is very small, it goes like the probability square, and so on and so forth. You can do a very nice exertion set exercise to prove that. So basically what I'm trying to tell you is that even though the power spectrum, the curvature perturbation is flat, you're going to form primordial black holes with the smallest mass possible. So corresponding to the horizon of order of k short here in terms of moving momenta. So here is the mass function of this corresponding mass distribution. And here, of course, we set things in order to have that the total FBBH, which is the area of this blue curve, is going to be equal to 1. So we will require that all the dark matter is in the form of primordial black holes. Then there is a second peak, even though tinier, which comes from the fact that during the QCD phase transition, which is a second order or even not even a second order, then what happens is the following, that you have the equation of state is changing slightly, the sound speed is changing, and then you have the threshold to form a primordial black hole is also lowering a little bit, so it's easier to form a primordial black hole. But in any case, you have a spike, which is identified by the chi-short, and then you have a characteristic power spectrum that goes like, if I remember correctly, goes like 1 over m to the power 3/2, depends on which notation you use, which formula you use to define this FBH. Okay, so now what is interesting is that if you look at the omega, as I told you before, omega is proportional to the, at least on the right of the peak, to the power spectrum square, so it's very flat. So here we of course set the amplitude of the gravitation of the power spectrum of the curvature perturbation in such a way to fit the nanograph data. So that's the rule of the game, of course. And then what is the reason why we also chose enormous flat power spectrum is we ask ourselves, suppose that this signal is in fact stochastic gravitational wave background, how can we check it? So the answer is maybe we can extend the power spectrum to intersect other experiments which operate at much larger frequencies, which in this case is basically LISA. And then, of course, at some point, the K long is met, and then you just simply go down. So this idea can be, in fact, can be double checked by also LISA. So that, of course, we did it by hand. The fact that the power spectrum has to be flat enough in order to be tested by another experiment. Last transparency is just to tell you that, in fact, after we wrote this paper, there was a group by Kusenko et al., which pointed out, in fact, that there is already in the HCC, which is this hyper supreme camera, which is looking for micro lensing around the same range of masses. Apparently, they claim they've already seen a signal, a micro lensing signal, which can be ascribed to a primordial black hole in the Andromeda galaxy, and they say that, in fact, so here this is the the figure taken from their paper. The green region is the region that we predicted, and the region here is violet is the region which is an agreement with this potential signal. Only one event so far, because the experiment is not working right now. They're waiting to have a green light to take more data, and apparently, what they claim is that this event fits perfectly the mass function that we came out motivating the nanograph results. In the future, if they have more time to take data, this region will collapse, that will be allowed eventually, will be collapsing into this red region, which overlaps again with the mass function that we found. Okay, so conclusions is very simple. We proved that, or we gave a suggestion that the nanograph 12.5 year signal, in fact, may be consistent with the primordial black hole hypothesis. And if that is the case, the primordial black holes can be really a total dark matter. And I believe that's interesting because, of course, if that is the case, it means that we don't have to invoke any particular, exotic candidate for explaining dark matter beyond the standard model. So, and I will stop here. Thanks a lot for your attention.
Thank you very much, Tony. Very nice talk, and curious coincidence, right? This last observation that you mentioned. Please, we have a question by Diego.
Ciao, Tony. Can you explain when you extend this flat plateau, you could also cut it before it is. Yeah, what can you say again? What fixes the length of this plateau to the right or to the left?
So as I said, well, I hope I was clear. So we could have, of course, taken a tilted power spectrum in this region and still fit the nanograph data. But then, of course, what we wanted was to extend it up to entering the LISA band. So it's an ad hoc required.
Yes, but physically it is the tilt of, I mean, what determines this?
Physically, it is the tilt of the curvature perturbation power spectrum.
Okay.
That you have to change in order to change the tilt of this signal. Yes, because as I was showing before, so that's a key point. Yeah, so that's a key point. You see, so the 2-point correlator is really proportional to the square of the power spectrum. So if you take a power spectrum which is basically flat, then this is reflected in the omega. Okay, so that was the rule of the game that we used.
Yeah, you can also, in principle, fit it to the right. I mean, you could also start it. If you don't want to fit nanograph, you could also start a bit more to the right. No, I mean, these scales are a bit flexible, right?
Yeah, it is completely flexible. It's up to you how to choose the tilt. Yes.
Okay, thanks.
Mm-hmm.
Any other question for Tony? Okay, let me ask one in the meanwhile. So related to what Diego just asked, so this would mean this would connect with the duration of this phase in the inflaton potential in which you exit slow roll.
Yeah, exactly.
Suppose,
so
ultimately,
basically this K long, K short. So it depends which model which method you use. So if you use this ultra roll non-attractive phase, it will correspond to the length of this case. Of course, that's not the only option you can invoke. So in this kind of business, basically the initial condition that you put, you write down the curvature perturbation that you want, and then only afterwards you ask yourself how to produce it. But there are, I mean, in the paper we have 2 or 3 examples where we indicate how to produce it. It's not, I mean, it's not difficult. I mean, it's model dependent, of course. I mean, nobody's hiding it. It's simply you input what you want, and in order to get out what you want, of course.
Okay, thank you. I don't see any other question. So in that case, I would like to thank very much all the speakers of this morning. And we reconvene for the cosmology session of contributed talks at 2:30